We've spent the past two lessons reviewing all the integral techniques that we've learned so far. We went over U substitution, the basic power rule, trig rules, inverse trig rule, rules for natural log and e to the x, and so on. Now, today the goal is to be able to just look at one at random and figure out which rule we need to use. Now that may seem crazy, but it's not. And it's really more how the normal world works. Okay, if you've ever watched the show House, I know it's a little older now, but um, when the patient comes in, they don't tell the doctor, "Oh, well, this is what I have, and this is how you should treat me." He's got to figure that out. He's got to diagnose the problem. He's got to decide the tests to run, and he has to decide the course of treatment. He has to look at the symptoms of the patient and figure that out. And we have to do something similar here. Granted, I'm not arguing it's quite as important as figuring out the symptoms and treating a patient, but the process is really similar because you have to look at the symptoms or the qualities of each problem, look for key things, look for red flags or markers or things that'll trigger in your brain what you need to do, and figure out what method you need to use to solve it. One thing I wanted to show you is this. This is not perfect by any means, but it just kind of gives you some general guidelines. This will be posted on my school website if you want to see it there. It just kind of gives you some good questions to ask yourself if you're not feeling sure about how to approach an integral. So this just gives you a flowchart of questions. So for example, you first say, okay, does it have trig? If it does, and you say yes, then the next question you ask is, okay, do I just use the basic rules? In other words, is it one of the rules you have to memorize, like secant squared x, or negative cosecant x, cosecant squared x, or whatever? Is it one of the basic rules? If it is, then just use those rules and you're done. If it's not, then you need to try U substitution. And U will either equal the denominator, or something inside of a power, or a radical, or something along those lines. Okay, if it doesn't have trig, then the next thing I would look for is e to the x. And if it has e to the x, then you just do one of two things. If it has one e to the x, you'll make u the exponent. If it has more than one e to the x, you use more basic trig rules. Now, if it doesn't have trig or e to the x, then you've got to go and think about it differently. You ask, okay, can I just use the basic rules? And if so, well, does it need to be simplified first? Perhaps you need to distribute first, or if there's a single term on the bottom, that's one of those symptoms or red flags you need to look for. Can you just split it up or bring it up and distribute? And if that won't work, if it's not basic and you can't rewrite it to be basic, then you need to try U substitution. If U substitution doesn't work, and occasionally it won't, then our other options are inverse trig. That's going to happen when your exponent is bigger on the bottom, and it's usually going to be different by more than 1 from the top. In other words, the top might have no exponent and the bottom has x squared. Or the top has x squared and the bottom has x to the 6th. So they're drastically different exponents. Or if the power is bigger on top or equal on top, then it's probably going to require long division before you can move any farther. So again, this is not a perfect flowchart. It's not a end-all or catch-all that'll just solve everything for you, but at least helps you ask the right kind of questions and gives you some hints about the markers. So again, this will be up on my website if you want to use it or make a copy of it. Alright, so that being said, let's look at these three, because they're really quite similar. If you look, their denominators are all three the same, x squared plus 9, and they all have a 4 on top. But simply by changing what power of x I have on top, it drastically changes what method I use for each one. Okay, if we look at the first one, we are going to solve each one of these. If we look at the first one, 4 over x squared plus 9, U substitution is not going to help us here, because if we say u equals x squared plus 9 and then du equals 2x, we've got a problem, because we don't have an x on top. We've got nothing we can work with. So U substitution fails us. So if you can think back to the flowchart I just showed you, I pointed out that if the exponent is bigger on the bottom, then it's probably a good idea to try inverse trig. So this does look kind of like an inverse trig. It looks like the form of arctangent. So I'm going to try that. I'm going to say du over a squared plus u squared equals 1 over a arctangent of u over a plus c. Okay, tell you what, we'll move these over and, whoa, sorry about that. We'll just delete these for now, and we'll do them on the next pages. Remember, a, no matter what order it's written in, a is always the constant, so a squared is actually the 9. A squared goes with the 9, and u squared goes with the x squared. So then I simply take the square roots to get my a and my u. Square root of 9 is 3, square root of x squared is x. And then I take the derivative of u to get du. So that's 1 dx. Okay, the du doesn't quite match, but we can fix that because it says du should be 1 dx. We have 4 dx, so we need to multiply both sides by 4. That we can do. Coefficients we can fix. So we have to put a 4 in front of the du, which means we need to put a 4 over here. So we actually have 4 over a, so that's 4 over 3, arctangent of u, which is x, over a, which is 3, plus c. Okay, now if we just change that a little bit, if we just change it to be 4x over x squared plus 9. Well, let's try u substitution again. U equals x squared plus 9, du would equal 2x. Hey, we do have an x this time. In fact, the only thing wrong is the coefficient. We're allowed to fix that. So we multiply both sides by 2, and then we match exactly. We have 4x. So I come over here and I'm going to put the 2 out front, and I'm going to get du over u. If you recognize that rule, it's the natural log rule. So I'll have 2 natural log of the absolute value of u plus c, or 2 natural log of the absolute value of x squared plus 9 plus c. Two quick things about that answer. That answer is great, nothing wrong with it. But just keep in mind you wouldn't have to write the absolute value signs here because x squared plus 9 is positive always. Also, you could move that 2 up as an exponent. So it could be written like this as well. Both answers are completely correct. Just trying to make sure you remember that those are equivalent. Okay, and then we just do a slight change. And we have 4x squared over x squared plus 9. And u sub fails us again, just because we changed the exponent on top. Because if we tried u equals x squared plus 9, du equals 2x, well, we can't change x to x squared. We can change that 2 to a 4. We're allowed to fix the coefficient, but we can't be messing with the x's and the exponents. So it's no go. Okay, so if you remember, if we said if the powers were the same or bigger on top, then we probably needed to try long division. Okay, and I would recommend doing what you just saw me do. If you have terms that are missing, whether it be an x term or an x cubed term or just a constant, put zeros there just to kind of help you keep things lined up. So the first step is to divide. X squared goes into 4x squared 4 times. Next we multiply. 4 times x squared, 4 times 9. Then we subtract 4x squared minus 4x squared, nothing. 0 minus 0, nothing. 0 minus 36 is negative 36. X squared will not go into negative 36, so that's our remainder. So we have negative 36 over x squared plus 9 is our remainder. Okay, so we can rewrite it now. Instead of 4x squared over x squared plus 9, we can write it as 4 minus 36 over x squared plus 9. Okay, now I'm not going to solve this one all the way out just for the sake of time, but the antiderivative of 4 is 4x. And this second part is another inverse trig problem. It's another arctangent problem. And if I'm doing this correctly, it's going to be 12 arctangent of x over 3 plus c. I'm fairly certain that would be right. So you'd have to bring the 36 out front and then divide by your a, which is 3. So that should be good. But the main thing I wanted you to see there was the long division. Alright, so there we compared 3 very similar problems and showed you how to separate which one was which and what method to use with each one. We've just got 2 more we're going to look at. Okay, I'll go ahead and tell you, this is going to be U substitution problem. What makes it difficult is it's not really clear what in the world to choose for U. Well, if that's the case, just try a few things. To me, I would say there's three possibilities. U could equal cotangent, U could equal sine of x, or U could be the natural log of sine x. So those are our options. So let's try each one of them and see which one makes the most sense. Well, the derivative of cotangent is negative cosecant squared x. So let's see. If I plug U into cotangent right there, this looks nothing like this. So that's no good. Not going to work. Okay, if U is sine x, then du is cosine x. So if I plug sine in there, I get natural log of U, okay? And cosine is not cotangent, so that's not a match either. So that's no good. So let's hope this last one works better. We have natural log of sine x. Remember, the rule for natural log when you're taking the derivative is the derivative of the inside over the inside. And if you remember, cosine over sine is the same thing as cotangent x. Okay, now this looks promising, because if we take this, replace it with u, then that is a perfect match for our du. So we actually end up with just u du, because the natural log of sine x gets replaced with u, and the cotangent x dx gets replaced with du. So then it's a simple power rule problem. Add 1 to the exponent, divide by that number, and we get 1/2 times u, which is natural log of sine x, all squared, plus c. So please, don't be afraid to just try some things and see if it works. There's nothing wrong with trying it and getting it wrong. The key is to just be able to recognize when it is wrong and that you need to try something different. Okay, last example. Just wanted to remind you of this. Anytime you have a natural log, it's going to be your u, which really would have helped us on this previous one, right? So anytime you see natural log, you're going to use it as u. So natural log of x cubed, we get the derivative of the inside over the inside. Okay, well, we can cancel out 2 of the x's, which just gives us 3 over x dx. Okay, well, if you come over here and rewrite this, you don't have to rewrite it, but this may make it easier to see what's going on. We don't have 3 over x, but we do have 1 over x. So we can fix it by just dividing both sides by 3. That gives us 1/3 times the integral of u du. Again, it's just a basic add 1 to the exponent, divide by that number. So we get 1/6 times natural log of x cubed squared. Okay, now one warning. Because of the properties of logs, there's lots of different ways this could be written. Because if you remember, this 3 up here with the natural log could be brought down front. So this could be rewritten like this. In that case, you could go ahead and square the 3 and make it a 9 and pull it out. Make it 9/6 or 3/2. So just be wary of that there's lots of different ways this could be written legitimately. Okay, the practice for this is going to come from page 486 in your book. So that's a great place to practice and to see if you can figure out what method to use when.